Okay, it is time. 4 o'clock. Welcome back to your favorite class, of course. Thank you, Mr. McDonald, for coming through for me. Right. So, good job on the exam. Holy crap. You guys took that thing out to the back shed and bam, killed it. The average on the test was at 84, multiple hundreds. Damn, really good job. I mean, I didn't think that was I didn't think it was an easy test. Like, you had double integrals, you had, complicated friction problems, belt friction. Yeah, you guys, I was really impressed. Good job. All right. Keep that up. Don't rest on your laurels, rawr, etc. Okay. So let's move forward then. Topic today, we're going to talk about rectilinear motion, finish our rectilinear motion. Then hopefully we'll get into the curvilinear motion notes, which I also posted this morning. So yes, that's where we're going. I posted a new homework as well, homework number 5. That's going to be due next Tuesday, so a week from today. 6 problems, a couple more than normal because, you didn't have homework last week, and I'm trying to kind of keep you on track. So take a look at that when you can. And if you have questions, office hours every day, 8 a.m., 9:30 a.m. So do that. How do we like the funny today? I wanted to post a joke about sodium, but was like, nah, people won't understand. Get it? Get it? Because sodium is in it? Get it? Okay. I like this person that responded. Post it anyway. Most people are smarter than you are think and will probably understand it. So, yeah, I bet you didn't see that. Smarter than you are think. I didn't see that the first time I read it. Then I read it again. And yeah, kind of funny. My English is better than you are think. Okay. Right. So anyway, that one's pretty good. Let's continue with our dynamics discussion. Okay. That's not this class. That's not this class either. Yikes. Okay, well, we're just starting new. I'll just bring in the PowerPoint slides here and we'll kind of review what we talked about last time, about where we left off. So we were looking at one-dimensional rectilinear motion. And we had written a series of equations that were relating position, acceleration, velocity, and time. And so to kind of recap quickly, rectilinear motion, sort of your review. Pretty much the basics come down to the following, that the velocity is the derivative of the position vector, that the acceleration is the derivative of the velocity vector. These are the bread and butter for this portion of the class, okay? We had simplified and looked at a variety of different situations where acceleration was a function of time, acceleration was a function of position, could be a function of velocity, all these sorts of things. We looked at a lot of special cases, and you can dive in on those for homework. So you're going to have some homework questions where, for instance, like acceleration is a function of position. So for like something escaping the Earth's atmosphere, which is interesting. So a little bit of complication, but all in all, everything is more or less coming from these very simplistic looking equations, even though there's a lot of detail there, right? We also looked at what happens if acceleration is constant. And we looked at equations that occur if you simplify and have constant acceleration. And so specifically, we saw something like, this is constant velocity, sorry, I want constant acceleration. That the velocity, if you have constant acceleration, is v naught plus at. And we derived that particular guy, showed why we had to have constant acceleration so that we could pull it out of the integral in a very specific way. Another favorite from your physics class. We saw this guy, and that was derived using velocity as dx dt in conjunction with some previous information. And finally, we also saw a relationship between velocity, acceleration, and position, which was velocity squared is initial velocity squared plus 2 times acceleration x minus x0. So those are some other pretty standard equations. You've probably seen these in your elementary physics classes. This is specifically in one dimension. Usually you're introduced to these in high school physics when you're talking about acceleration of gravity, particularly in 2D motion. But here we're just kind of talking about 1D motion. We actually derived these guys by pulling accelerations out of the integral and looking at what was going on there. Okay, so that's for one specific particle. And now I want to talk about sort of the next step in rectilinear motion of particles, and that is to talk about the relative motion between two particles. So that's where the lesson kind of starts today. All right, motion of multiple particles. Kind of like the snow out there today. It's kind of nice walking in it. It's kind of like serene and calming. Hey, I'm enjoying it out there. All right, so motion of multiple particles. Specifically for now, we're going to stick with 1D. And to start, we'll talk about independent motion. And what I mean by that is two particles that can move freely and don't have any relation to each other. And start with independent motion. Meaning that the position of particle 1 does not depend in any way on the position of particle number 2. All right, so let's consider now two particles that are moving in this one-dimensional space. Okay, and let's say that we have particles located at position A and position B. Okay. So if we kind of go with our typical sort of number line style, we have some origin and some general like x direction. So let's call this over here the origin, and we'll say that we have some general x direction. We're going to say that we have some particle that's moving along this one-dimensional direction. That's particle A. And some particle over here, also sort of arbitrary in space. Let's call that particle B. We know sort of from our discussion previously that we can locate those guys in space using a position vector. And so we could say that, for instance, here's our position vector locating A. Something like that. And we can also have a position vector that locates B. I would say this is my position vector R locating B. Nothing too crazy here. What we're interested in is if one of these things is moving or these things are sort of moving independently, can we come up with some relationships between their velocities and accelerations that might help us learn something about their motion? Okay. And the way that we start is we talk about or describe the position of one particle relative to another. And so we'll say here that the position of B relative to A would be the position vector R, which arrives at B from A, and it has this general direction. I read this as the position vector arriving at B from A. Some people say it's the position of B relative to A. However you want to think about it, however you're comfortable is fine. But I'll say here R, B, A is position of B relative to A. And we can see mathematically that pretty easy to come up with a relationship between the position of A, the position of B, and the position of B relative to A. And that would be that the position of B relative to A is the position of B minus the position of A. I'm doing this all in vector form right now because we're going to use this in 2 dimensions later. So I'm sticking with sort of vector notation for now. may also be written as, and probably is more often written as, and I'll give this one the box. Rewriting so everything is positive and everybody is happy. Position of B relative to A plus the position of A. Everyone's happy when there's no minus signs. Okay. There's not much to the next step here, so I'll just go ahead and present it. And we know this generally to be true if we're in one dimensions, is that if we have this general relationship between their positions, then if we just differentiate their position instantaneously with respect to time, then we can just simply say that the velocity of B is the velocity of B relative to A plus the velocity of A. So can differentiate. Oh God, spelling is hard. So with respect to time here, and you can come up with relative velocity and acceleration equations. All right, and that would be that the velocity of point B is, I'll rearrange here, the velocity of A plus the velocity of B relative to A. Okay, so that would be your relative velocity equation. And we also have that the acceleration of point B is the acceleration of A plus the acceleration of B relative to A. I don't think anything too crazy so far with these particular equations. If you happen to know some expression that gives you the position vector as a function of time for each one of these guys, very similar to like what we've seen so far, you know, the particle moves as some function of time, can differentiate that expression a couple times to give you the velocity and acceleration of those particles as a function of time. And if you happen to know what those are, you can relate them through these relative velocity equations. All right. So let's look at an example where we're maybe leveraging some of these ideas. This is an example from the notes. I'll just copy paste this right in here. You have a homework problem very similar to this, I think number 4 from your homework. The classic 2 automobiles on the highway problem. Classic. All right. Autos A and B traveling in adjacent highway lanes. Very important because we don't want them running into each other. All right. At t equals 0, have positions and speeds shown. All right. So at this particular instant, car A is look like standing on the origin or driving at the origin location, and car B is 75 feet right of the origin, and they have various speeds. Knowing that automobile A has a constant acceleration, important, and that B has a constant deceleration, determine when and where A will overtake B and the speed of each automobile at that particular time. Okay, so let's go through this and see what we come up with. There's two kind of ways to solve this problem. I guess there's a couple ways to solve it, but I'll give you a second to sort of finish writing this down. But since we have constant acceleration equations, we could just come up with some general expression for the position of A and the position of B as a function of time, and use that information to sort of answer our questions. But here I'm going to leverage some of the relative acceleration, velocity, and position equations to make our life a little bit easier in the process. So let's put that into words, what I just said, okay? So could use constant acceleration equations. Here for each vehicle. And so what I mean by that is you could have something like the position of car A is equal to the original position of car A plus the original velocity of car A times time plus 1/2 acceleration of car A times time squared. You more or less have all of these things. Sorry, I should be more specific here. The initial velocity, car A at time t, along with this information. Kind of work those guys separately and use the information garnered by both of these equations to make your way through the problem. That would be not that hard, okay? Probably something you might have done in like elementary physics class, the classical two cars driving down the highway together, right? All right. Cool, fine. You could do it that way. You have all of these things, right? Like the final position of A, you know, might be something you solve for later, but initial position, obviously you can see it's at location 0. Initial velocity given, acceleration of A given. All these sorts of things are given, okay? Instead, I want to try and leverage our relative velocity equations. Okay. You'll see the power of this in just a second, okay? So what I mean is I want to do like the position of B relative to A is equal to the initial position of B relative to A plus the initial velocity of B relative to A times time plus 1/2 the acceleration of B relative to A times time squared. Instead of kind of working both of those equations above independently, maybe we can do something that looks a little bit more like this. Okay, so let's go ahead and work through this. Let's define each one of these. For instance, the position of car B relative to A. Here, that's like the position of B minus the position of A. If we're interested in the original position, then we can simply come up to our picture here and see that car B is 75 feet in front of car A. So the position of B relative to A initially is 75 feet. Now, in solving this problem, what I'm interested in first is when and where A will overtake B. So what will the position of B relative to A be when car B overtakes car A or car A overtakes car B? 0. So at time of interest, my position of car B relative to A is going to be 0. They're going to be right on top of each other. I want to know that point when they're overlapped. All right. Next up, I'm going to look at this sort of velocity term here. So the initial velocity of B relative to A would be the initial velocity of B minus the initial velocity of A. I'm sort of neglecting vector notation here for now, just assuming all one-dimensional I hat. All right. Okay. So I need initial velocity of B, initial velocity of A. Okay. So here's initial velocity of B, 36 miles an hour to the right. Here's initial velocity of A, 24 miles an hour to the right. Okay. So this here will be something like 36 miles per hour minus the initial velocity of A is 24 miles per hour. Obviously, this is 12 miles per hour. I'm going to convert on the fly here to feet per second. That's because we're going to use feet and seconds in this problem. So 12 miles an hour in feet per second is 17.6 feet per second. So we're making our way through these variables here. Continuing here, let's look at the acceleration of B relative to A. Here, this is the acceleration of B minus the acceleration of A. I'm told some information about their accelerations in this problem, namely that the accelerations are constant. So again, not going to depend on time here. That's why we have these constant acceleration equations we're using. And the acceleration of car B is told decelerating at 1.2 feet per second squared. It's kind of in the problem up here. Deceleration of 1.2 feet per second squared. So I'll include that as a negative value. So here, negative 1.2 feet per second squared minus the acceleration of A. A is positive, but we're subtracting here. 1.8 feet per second squared. So here, the acceleration of B relative to A, something like negative 3.0 feet per second squared. So that means basically if you're driving in car A and you're observing car B, it more or less looks like it's accelerating towards you at 3 feet per second squared. Even though if you were kind of standing still on the side of the highway and looking at car B, you'd only see it decelerating at 1.2 feet per second squared. That's all kind of, you know, your frame of reference and how you're sort of viewing this problem. All right, so we're ready now? Solve for t in the equation above. Okay, so our final position of B relative to A is the location 0, so they're right on top of each other, equal to the initial difference between the two of them, 75 feet, plus the initial velocity of B relative to A, that's 17.6 feet per second, times the variable time, which we're looking for in this problem, plus 1/2 the acceleration of B relative to A, which we just said was negative 3 feet per second squared, times time squared. This is quadratic in t. You can use your favorite opposite of B plus or minus the square root of B squared minus 4ac over 2a equation. It's my favorite. And you'll get two possible answers here, negative 3.3 seconds, which doesn't really make any physical sense, and 15.05 seconds, which obviously is our answer here. Okay, so that's kind of like making our way through part A of the problem. Part A asks us when and where A overtakes B. Well, we just figured out when, which is helpful. Once we have the time, things kind of ease up and our life becomes easier. We can use either constant acceleration equation for either car A or car B and the associated time to determine the position of each one of these vehicles at that particular time. So now with time, let's, for instance, just use information about car A. And now we're interested in what is the final position of car A at some time. All right. Obviously, our initial position for car A, it's right on the origin of 0. So we're going to have something like the position of car A is the initial velocity of car A. The initial velocity is given as 36 miles per hour. Is it 36 for A or 24 for A? I can't remember. 24 for A. So 24 miles per hour, just as a side note. In feet per second is going to be 35.2. As a side note. So here we have 35.2 feet per second times our time plus 1/2 the acceleration of A. We're given in the problem initially as 1.8 feet per second squared times time. And we're going to plug our time variable in here from above. So we can use our 15.05 seconds here to get us to that answer. So with t is 15.05 seconds, then you get that the position of car A, which we know at this particular time is the same as the position of car B, it's sort of what we solve for at this particular time. This is going to be 733.6 feet. Okay, finally, sort of part B of this problem is what is the velocity of each one of the vehicles at that particular time? Again, we'll lean on our constant acceleration equations. One of them being the equation that relates velocity, time, and acceleration. That would be the initial velocity of A plus the acceleration of A times time. So the initial velocity of vehicle A, 35.2 feet per second, plus the acceleration of A. This guy's speeding up at 1.8 feet per second squared. Times time, 15.05 seconds. Where we would have that the velocity of A at that particular time is going to be 57.8 feet per second. Or if you want to convert back to miles per hour, 39.4. Okay. Same process for velocity of B. I'm not going to write it all out. I think you guys get the gist. is at velocity b, 34.7 feet per second. Or if you want it in miles an hour, 23.7. If we're going on the highway, they're kind of going a little slow. Definitely think they're in the right lane. I guess they're just trying to instill, you know, be safe on the road by going 40 under the speed limit. You ever see those people on the highway that are going like 20 under and you're like, dude, you're about to get someone killed, man. Like, oh, it drives me crazy. All right. So some interesting power, some interesting leveraging here using our relative position equations or relative position ideas. And again, you can kind of like stick them right into those constant acceleration equations and they'll end up working fine. Like I said, you could have gone through this process here with these two equations and you'd have sort of two unknowns in this situation if you want to think of a third equation being xa equals xb, sort of eliminating that sort of ideas, you would equate these two equations to each other and you could be on your way with that idea. But just equating these two equations, saying xb equals xa and equating those two things, that basically transforms it into sort of this equation here, right? So you kind of see the power of the relative position equations there. All right. Now, next part of the lesson. In the previous example, and sort of what I talked about so far, all those particles are moving independent of each other. Okay. So vehicle A and vehicle B don't really depend on each other. Their motion is independent. If I want, I can speed up my car, slow down my car. Doesn't matter what the other guy's doing, okay? So the next lesson we want to talk about is dependent motion. And what we're going to look at looks kind of to be like two-dimensional motion, but it's actually one-dimensional motion. So let's talk about that next, and that's dependent motion. Okay. And so previous examples, particles were moving independently. You guys like my new do? I was grading your exams and all my hair was falling out, and then I looked in the mirror and I said, oh my God, all my hair fell out. You guys are stressing me out that much. No, I'm just kidding. Your exams were good. All right, previous examples, particles moved independently. So what about a situation where particles are sort of moving together, have some dependency? So now, what about dependent motion? Okay, and the El Clasico example, just like the two cars on the highway moving independently, the Clasico example for dependent motion is multiple masses hooked up to a pulley system. This is mass pulley system. The El Clasico. All right. So let's take an example here. Maybe you've seen something like this before, maybe you haven't. Okay, let's consider that you have some system that looks like this. I'm going to do my best to draw it. Here's your rope. All right. Okay. And let's say this guy is connected to the wall. All right, he's connected to the wall. And you've got some mass that hangs off this guy. And you've got some mass that hangs off this guy. The classico problem. And let's say that this mass is at A, and this mass is at B. All right. This is a situation of dependent motion, because if A moves, B will move. And so you need some sort of way to define how A and B are like moving relative to each other to sort of learn some information about what happens to B if you do something to A. All right, so this is the classic system. So can we determine position, velocity, acceleration of B given info about A? And how might we do this? Well, the method here, when you're looking at like these mass pulley systems, is sort of the following. You want to set yourself some datum, and usually it's easiest to define either the ceiling as the datum or maybe one of the pulleys as the datum. Okay, in this situation, let's just set the datum as the ceiling. Okay, so let's define then the position of A as like XA, and we'll define the position of B as XB. All right. I want to make one more definition here. And let's say that we have this guy, G, that's the point where the rope is sort of running into the wall. All right. So we'll define here, we know that the thing or the background information that's sort of governing the dependent motion here is that everything here is connected by like one rope, okay? And that rope, unless something strange happens, cannot change length, right? So the method here, you're defining your datum and understanding that the length of rope cannot change. So the idea here is we want to write rope lengths in terms of positions of points of interest. Okay. So in our example here, we might say that the length of rope AG, which is kind of, you can sort of see from the picture here, it starts at A, wraps its way around, ends at G. I might want to define one last thing here. No, we'll leave it there. That's fine. Yeah, no, we should define this. I'm going to call this distance here delta. To sort of this first pulley. It'll make sense in a second. Yeah, well, I'll just leave it as it is. So the length of this rope is approximately the length out to A So this, more or less, this portion of the rope here, plus what is this portion of the rope, which is approximately XB, plus again, we have a similar portion of this rope, which is again XB. So for all intents and purposes, this is 2XB. A little bit more on that extra information of rope just to come in a second, but for now we can approximate the length of this rope totally as the length to position A plus 2 times the length to position B. All right. Now, if I were to think about how B and A are moving relative to each other, I would think about, all right, if I changed the length of A some small amount, how much would the length of B change? So if I increment XA by some small amount, delta XA, what happens to the position of B? All right, so let's do that. So we have LAG. This is going to be equal to my new increment. Let's say I'm moving it down slightly. Plus 2 times. Something's going to happen with B here. So let's say that it responds with some change, delta XB. I'm interested in the relationship, more or less, between changing A, what happens to B? Well, my length of rope doesn't change. This LAG we just said is going to be consistent. So what that means is I can more or less equate whatever my initial amount was, XA plus 2XB, to this final amount, which is some incremented amount that I pulled in the direction of A. So we can equate. If we call this star, call this double star. You'll end up with XA plus 2XB equals XA plus delta XA plus 2 times XB plus delta XB. Okay, pretty easy to see that only the increments are really going to make a difference here. And, you know, this XA is going to cancel this XA, 2XB will cancel this 2XB. And you're going to end up with something like 0 equals delta XA plus 2 delta XB. Or the change in row B is going to be negative 1/2 the change in A. So B is moving up, or moving the opposite direction, half the amount that you moved A. Okay, so if object A moves by an amount delta XA, object B moves half that amount in the opposite direction. So that's one way that you could sort of figure out what's happening with this dependent motion, this classic mass and pulley problem. Now, obviously, these relationships are going to change with each mass pulley system that you have. Okay, so all these mass pulley systems that these people think up, that I don't know if I've ever seen in real life, they're going to vary. So how long the ropes are, where your datum is set, how many pulleys there are, where the masses are, etc. So relationships will vary by problem, but that's the general strategy. right? But the general strategy will still remain the same. All right. Now what about the velocities and accelerations? And so let's reconsider our previous situation. And previous example. You had something like the rope length, AG, is the position of A plus twice the position of B. It's your general relationship that's got to hold because the length of the rope stays the same. Okay. Well, if I just took the derivative of this, I will end up with the derivative of the length of rope as a function of time equals the change in the position of object A with respect to time plus 2 times the change of the position of B with respect to time. What's the derivative of the length of rope with respect to time? How much does the length of rope change as a function of time? Yeah, nothing. Since this rope is a constant length, the length of the rope does not depend on time. The length of the rope is what it is, unless you have some magical rope that like you got from Jack and the Beanstalk that just keeps growing and growing and growing. That length of rope is not changing at all. We can identify these guys as well as things that we know, things like the velocity of object A, and here things like the velocity of object B. So in this particular situation, you have something like 0 is the velocity of A plus 2 times the velocity of B. Very, simple example. And you could even go one step further to get your relationship for acceleration. And that is here, the acceleration of A is 2 times the acceleration of B. This is an example of dependent motion. They're all hooked up on the same rope, on the same wire, right? And this is the general relationship that this one particular problem has, okay? So this is specific to this example. But strategy is the same. And the strategy is this. Set datum. Write positional equations. For us, that was like that would be one example. If you have multiple ropes, you can write multiple positional relationships. And then differentiate for velocity and acceleration. That's the strategy. Okay. So let's take a break here. Come back at 5 o'clock, so about 10 minutes from now, maybe a little less than that. I'm going to put up an example problem here. And let's see if you can just sort of write the position, velocity, and acceleration relationships for this particular example. So take a break, stretch the legs, come back and see if you can come up with positional relationships for this particular example here. You guys do any of this like dependent position stuff in like physics class in high school or anything like that? No, not like this? Okay. So the classic pulley problem. What did they teach you a different method to like do it? Oh, that they like gave you from the book? Oh, okay. Yeah. So you didn't really have to like derive the relationship, you just gave them to you. There's a couple of different techniques that people like use to maybe come up with those relationships, like how many ropes did you cut through? That's got some indication of like some relative relationship between the two of them. I think this method works the best for how long the rope is in terms of all these variables. Did you get a chance to play your sax much or not? Okay, that's good. So is this at through MSOE or? So that, okay. Yeah. So you do this in the current center, like on that yeah, that where that circle track is or whatever. Yeah. Oh, that's got to be interesting. Uh, it's still fun to play. I mean, why do you think you would play anyway? It's funny. My brother, he's 12 years older than me. 45. He actually just had a birthday on Sunday. He's signed up for what they call School of Rock. He was in Cincinnati, and it's basically like this adult program where people who just like want to play an instrument, well, in, like with a group, can do it. So he just joined up, and he played trombone for a really long time, and kind of like learn how to play piano. But they just had a concert on this most recent Sunday, which happens to be his birthday, and they did that a roller rink, right? Where they were like, like these roller rinks for like, and it was a funk show, so it was like very appropriate. So like everyone was dressed up in like psychedelic '70s gear, and he had like bell-bottom pants. It was hilarious. Like it was so funny. And they sang songs from the '70s like "Freak Out." What are some of the other tunes, like '70s tunes that you would just know off the cuff, like Saturday Night Fever, just like all this stuff. It was really funny, but I think it's cool that he still finds a way to play like for fun. Yeah, let's see if I can find a picture. It's pretty funny. Oh, yeah. So this was their setup. Roller rink. Yeah. They had like a little disco light and stuff. That's my brother playing the keyboard and the bells on him. Very funny. Yeah. Anyway, if you were really into it, you can find a way to play. Then if you're 45. All right. I'm gonna walk a little bit. Okay, we're back. 5 o'clock. So in this example, basically all I asked you was to just write the position, velocity, and acceleration relationships between these guys. So, right, position, velocity, acceleration relationships. And I even already put in like the datum and the positions for you. Aren't I a nice fella? Okay. So in this particular situation, we only have this like one rope. Okay. And so let's just label this as like capital L. I mean, you could label it as like LAC if you want or something, but I'll just say rope length. Or the cable length is L. All right. So in this particular situation, we'll just go from there. The length of this rope is going to be something like XA. So it's like this first little bit of the rope. And I'll take this time right now to talk about some of the extra pieces of rope that we're not sort of accounting for here. So we say that here, this is the amount of rope that we have, and it's sort of governed by the position of this particular guy. So we just generally say that this position XA goes to like, let's say the top of this particular piece. But we could also say that it like goes to that location, which is the center of that pulley. It would be like the same equivalent thing. Lots of different ways to sort of go about this, but you know, generally the position to that location is given by XA, and this segment of the rope is approximately given by that. This next segment of the rope here, which is where we're going to sort of go to next to consider, is also given approximately by XA. And what you might say to yourself is like, well, what about this extra bit here? Okay, because that's really not included in what is XA. How do we deal with that, or how do you reconcile that? Well, you can reconcile that by understanding that that is just a constant length. Okay, so if you want to really get technical about this and really consider this, you might say that, all right, let's call this little bit of extra space here. Let's just call that delta, right? And so then you'd say that our rope length is, okay, it's this XA that we just talked about. And then this next bit is, okay, let's call it XA minus delta. And let's see what happens. All right. This bit of the rope is going to be something like XB minus delta. This bit of the rope is going to be XB minus delta. So something like plus 2 XB minus delta. And then this last little bit of rope, this little bit of guy here is going to be plus XC minus delta. Okay, so we got all these like little deltas roaming around. The point is you're going to end up with something that looks like some constant value L, which whatever the length of the rope is, we don't necessarily know at this point. XA plus XA plus 2XB plus XC minus here what is 4 delta. Right. So if you wanted to sort of rearrange this, you might write this as L plus 4 delta equal 2XA plus 2XB plus XC. And here's sort of the point, is that delta value is a constant value, okay? And on the left-hand side, originally, we just said some variable was the rope length L, some constant number. We know it's unchanging. Well, the value of delta is also not changing either, okay? So if you wanted to reassign this as a new variable, let's call this a new variable L prime, fine. You're still doing the same thing. Your analysis is still basically the same. Got some constant value on the left-hand side, which is the rope length plus or minus some datum length of these pulleys, is going to be equal to what's the important bit over here, which is sort of the dependent motion of these guys relative to each other. And so that's really the takeaway here, is that you have some constant value on the left, which might be influenced by how far the pulleys are away from the wall, or what, you know, all this sort of random stuff, equal to really the meat of the problem, which is if I move object A, how do object B and object C move in relation, right? So if you're going to ask me to relate sort of a position-dependent relationship, I would write something here like L is equal to 2XA plus 2XB plus XC. This would be my general position relationship for this particular problem. I can differentiate this with respect to time to get my velocity. The length, or the length plus or minus some pulley distance delta. Regardless, it's a constant value. We take the derivative, it's going to be 0. And here's my relative velocity relationships for this problem. And one more time to get my accelerations. And here we are. So what these kind of problems boil down to is being able to understand that the motion of one object depends on sort of the motion of the other. And how do you use the geometry to come up with what's known as a constitutive relationship, or just a general geometric relationship between the objects of interest, right? So here, pretty straightforward example, pretty simple example. Now, let's put all this together with an example with some actual numbers. See if we can sort of bring this home. Okay. Here we are. Slider block moves to the right, constant velocity, 300 millimeters per second. Determine velocity of slider A. Velocity of portion C of the cable. Interesting. Velocity of portion D of the cable, and the relative velocity of C with respect to A. Bringing it all together in this one. I'm going to step away for a minute while you guys kind of copy this example down. I know there's a lot to this, so got to draw some pictures and write some stuff down. So give you a second if you're copying it down. I got to go do. Run out of juice. Quite a bit to this one. But the last couple of minutes, you're like, oh yeah, this slider stuff's easy. Yeah, bit more complicated now. If you're thinking about this particular problem and how you might want to attack it, it would be helpful to know that there's some fixed length that exists here between these two walls. This can help you on your way. Nick's over there looking like he's about to blow a brain cell, so just trying to help him out. Don't explode, okay? If you're kind of done copying the problem down and copying the picture, see if you can come up with an expression for the position relationship in this problem. But don't explode. Maybe another 30 seconds. I know there's a lot here to sort of copy down. Okay, let's give this a go. All right, so I want to determine the velocity of slider block A, given some information about slider block B. So we're going to sort of follow the strategy that I laid out before. And step number one in the strategy is to sort of obviously draw a picture. We have a picture, and then define a datum. And it's not so obvious looking at this particular picture what is the best datum. But I'll tell you, if you pick a datum that you know is not going to move and you stick with that through the problem, then you should be able to solve it just as well. I think the easiest point to select a datum in this problem is on the left-hand side, and that's where I'm going to work the problem, is here. And I'm going to select it obviously as like a vertical datum as opposed to kind of a horizontal datum, which we used in the previous like vertically aligned pulley systems. All right. You could make a selection for a datum here and also come to the same answer, but there's a little complication involved with that. I'm not going to go into the detail, but it's a little bit more complicated if you set your datum there. But since this is a fixed surface, it would be a suitable datum. You don't want to set your datum on a point that you know is going to move. That doesn't really make a lot of sense. So here we'll set our datum on the left-hand wall. Okay, now we want to define the positions of our individual blocks relative to that datum. All right, it's pretty straightforward. Here's like XA to block A. And then all the way out here, I'm going to have a position of block B. All right. So that's all I really got at this point. So let's see if I can go ahead and sort of define my position relationship. And when I define my position relationship, the method that I sort of described was writing the length of this rope in terms of the positions of A and B. So let's try that. All right. And let's just call this total rope length L. Okay. Or you could call it whatever you want. I'm just going to call it L. Okay. Now, obviously this first bit of rope, I'm going to start from the datum here. This first bit of rope, pretty straightforward. That length of rope is just going to be the XB. This next bit of rope that sort of contains point C here, that length of rope is XB minus XA. I think that's sort of obvious from the image here. But now I have a bit of a problem. And that is that I have to sort of define this length of rope here. But I have some issues in that I don't really know how to easily define that with what I have so far. Okay, how do we deal with this? Well, this is where I kind of gave my hint before, in that the fixed length exists here between the left and the right walls. And so let's let that distance between those two walls be a constant value L. If we can sort of keep things in terms of constants, we know when we take the derivative later to get velocity relationships that that's just going to turn into a zero, right? So that is going to help me sort of define the total length of this rope. So I'm going to add to it what is the length of this particular rope here, which is going to be something like plus this fixed length L minus XA. It's this next segment of rope here containing point D. And we see I have one more of those. So maybe I'll just make this a +2 times that quantity. So a bit tricky. You know what I'm saying? All right. So let's pull this out fully. you'll have an equation that looks like that once you multiply everything out. I'm going to rearrange this as L minus 2 little l is equal to 2xb minus 3xa. This here is your general position relationship that you would maybe strive to write on a test if you wanted to organize it well. Get constants on the left-hand side, get dependent positions on the right-hand side. Sort of just makes things easy to see and organize clearly. Now I'm ready to actually take my derivative and get my velocity relationship. And at this point, pretty easy to see. Here, this is my general velocity sort of relationship between block B and block A, given this problem. I think kind of in the previous examples, it was pretty easy to just see like what's the relationship between how the blocks are moving when you had those pulley systems. When I threw this one at you, it probably wasn't as obvious to just view this and see, okay, yeah, block A is going to move 3 times the rate of twice the block B. It didn't, at least it was not obvious for me to see that and understand that, right? So to kind of round out part A, we're given, not velocity of A, the velocity of B in the problem. So if the velocity of B given as a constant 300 millimeters per second to the right, so we'll take it as positive value. That means that velocity of block A is going to be 200. A second. Right. Both generally moving in the same direction. So a little bit tricky here trying to set this guy up. Tricky, tricky, tricky. All right, let's continue with the problem. Next, we're asked, what is the velocity of portion C of the cable? All right. Well, I'm interested in this particular point on the cable. And so let's just define a position that is XC to help sort of do that. So maybe, yeah, that's fine. We can just do it this way. I'll just do it right on here. Right up to that location. Right. So what I'm going to do now is I'm going to say that, all right, I'm going to use the same approach and say that there's some fixed distance of rope that exists from, let's say, the wall over here up to point C. And I can write that fixed distance in terms of the position of B and the position of C, and then differentiate that and determine the velocity, okay? So very similar strategy here for part B. Okay. Length of rope from datum to C is fixed. And let's call it the length of rope to point C, LC. Sort of makes sense to me. Makes sense, you heard? All right. So then, the length of rope to point C can be written in terms of our sort of like dependent position. Going back up to my figure here, it's just this length of rope out to point B plus whatever length of rope I need to get to point C. Okay. So it's going to be the length of rope to get out to B plus the length of rope to get out to point C, which here is actually the distance to B minus the position of C. Hopefully we can all sort of see that and understand that. Okay, take my derivative. That length of rope from the datum to point C, again, is fixed, doesn't change. So here we have 2 times velocity of B minus velocity of C. And if we know that VB is 300 millimeters per second, then quite simply, VC is 600. Right. Interesting. So even though that block B is moving 300 millimeters per second to the right, that one particular point of the rope, that rope sort of in the middle there at point C, that portion of the rope is moving twice as fast to the right. I would not really have intuited that personally. Maybe you can. Maybe you're better than me, I guess. It's hard for me to visualize that straight away. All right, next part of the problem. The velocity of portion D of the cable. All right, very similar strategy. I'm interested now in velocity of portion D. So we could do it in many ways. Again, considering the length of rope that's up to there, that's perfectly fine. I want to go with a little different strategy here, just for funsies, I guess. And we'll take this portion of the rope as a fixed length, just because we can. So maybe I'll redraw the picture down here for a little bit of clarity. So let me redraw the picture. And I'm making a cut at that particular location. That's where point D is. I know I have this fixed length L, which exists. I have the length out to A from the datum, and I have the length out to D from the datum. Similar strategy, the length of rope fixed between its attachment point at point A and the point D that we're interested in. Here we'll first be interested in like this portion of the rope, this segment. And we'll say that that is that fixed length script L minus the position of A. And then this length of the rope here is that script L minus XD. You could sort of come at it from the other direction if you want, but just kind of showing you some different methods here, some different strats, if you will. So here we are. Take our derivative with respect to time. And in this, sorry, should be V's. So in this situation, we're kind of get an opposite relationship between what's happening with block A and point D. So remember, we previously saw that the velocity of A, we calculated 200 millimeters per second squared, right? So that means that the velocity of D will be same magnitude, but acting left here. Or, you know, negative 200 millimeters per second if you want to think of like a global XYZ coordinate system, I guess. All right, last little bit here, leveraging our relative velocity expressions. Here I want the relative velocity of C with respect to the slider block at A. So what this is asking me here is, what is the velocity of C relative to A? So if I'm standing on point C and I'm moving with C, what velocity does A look like it has in my retrospect? Okay, so last bit of this problem. What is the velocity of point C relative to A? Well, we have equations for that. It's going to be the velocity of C minus the velocity of A. We've already calculated both of these. Velocity of C was moving 600 millimeters to the right. Sorry, millimeters per second to the right. Velocities, rawr. And velocity of A was acting 200 millimeters to the right, so we're going to subtract 200 millimeters per second. And we'll have that the velocity of C relative to A is 400 millimeters per second. So the idea here is if I'm standing on A and looking at point C, how is C moving from my general perspective? Well, point C is moving 400 millimeters per second to the right if I were to be standing on point A. Interesting. Think of it like if I'm driving in a car, you know, if I'm going 85 miles per hour on the freeway, which is about usually what I drive, and some grandma's going 50 in the right-hand lane, I'm cruising by here 35 miles an hour faster. So it looks like I'm moving 35 miles an hour to her, but in fact, I'm actually moving 85 miles an hour. It's interesting. Okay, I think we'll call it today. We'll start in on curvilinear motion on Thursday. And I would encourage you to take a stab at the homework, okay? You should be able to do the first 4 on the homework at this point. And after Thursday's lecture, you should be able to do the last 2 on curvilinear. So we will see you on Thursday, a little early today.